Thank you very much for that introduction. Thank you everyone for coming here. Thank you for the invitation. Having seen the previous talk, I wonder if a better recommendation would have been to have made no impact on hundreds of millions of users. Let's see. So I have this title of Data Summarization for Machine Learning, and full disclosure, I think the majority of what I'm going to talk about today is very much around data summarization, and the machine learning is a little bit more light touch. Think of it as sort of the end use to which you might put this summarization, and as I go through the talk, I'll say a little bit more about that as we go on. So again, Suresh did a wonderful, very thoughtful and nuanced job of thinking about where machine learning and more generally technology fits in with society. I'm going to take primarily sort of a computational view that thinks about what are the immediate computational aspects of this. So we'll start by sort of talking about what we used to call big data, what we now call machine learning or artificial intelligence. You know, we're very flexible in our use of terminology to describe the thing that we're doing. But what this means is sort of collectively over at least a decade and probably longer, we've made this argument that data is of increasing relevance, right? So if you go back to the early days of computation, there was maybe less focus on data and more focus on how do we get these computer things to work? How do we get them to add numbers together and not burn, right? You know, these kind of more sort of fundamental things. What is the expressive power and what are the kinds of functions and algorithms that we can compute? So now that, you know, the silicon substrate is more reliable, we can think more broadly about what can we actually do with reliable computing. We think, well, what are the things we can compute using data, right? The other part of this puzzle is the fact that as we deploy computation, you know, computation is no longer the mainframe. It's no longer the computer on every desk. It's the computer in every pocket. It's the computing device in every camera on every street corner, right? So collectively, we as a society are generating more and more data. And that gives us lots of potential, right? We can think about any aspect of society and how data and computation can influence that, both for good and maybe less clearly positive reasons. And that can be with any domain you choose. You know, it can be within the medical domain, and we start talking about you know, genetic sequencing, predictions, personalized medicine. You can think about social activity, social networks, identifying, you know, and predicting activities and outcomes. So, you know, all of this we can do. I'm going to take this as read because I think we're hopefully fairly comfortable with the specifics, and again, do that standard computer science sin of abstraction. Say, how do we abstract here? What are the common themes? We have large volumes of data, and those volumes are only getting bigger. And not only do we want to store and look up this data, but we want to make use of it. We want to identify what are the patterns in the data. We want to build models. We want to make predictions from those models. We want to choose which actions we should take. Right. So we want to do all this accurately and efficiently. So when we use this term big data, you know, there's a temptation to assume that the big solely refers to scale or volume. It's the sort of, often it's the most immediate thing that occurs to you. That's not the whole story. You know, when we talk about big data, often people refer it to mean about the big implications for society, the big impact it can have, the big consequences we might worry about. All that being said, today I'm mostly going to focus on these aspects of data volume, scale, and scalability. So if we think about computational scalability, we often get a picture like this one, right? You either from the inside of the data center, looking at racks and racks of computing devices and miles of network cabling, or, you know, one of these satellite views that show you how many 737s you can fit in a data center. And so that makes you start thinking about bigness. How big can you make your computation? Right? How do you take this multi-petabytes of data and scale up your computation? And there's a wealth of brilliant ideas that have been developed over the last decades to address this. Right? All kinds of different models of computation, different models of networking, different models of reliability and resilience, different models of data management. And with all of those comes some drawbacks. So whenever we think about this scale of computation, we also have to think about what's the cost. Right? How much kit do we need? How many miles of cabling? How many disks and CPUs? And we also have to think about the running costs. How much energy do we need? You know, as soon as we start thinking about how to locate a new data center, you know, maybe within the Arctic Circle to reduce our cooling costs, or next to a major waterfall so that we can generate cheap hydroelectric power, we realize we're sort of in a different league when we're talking about energy cost. So I'm not going to talk about that either today. What I'm going to talk about is something, sort of an alternative perspective. So when you've got a huge amount of data and you want to work with it, another thing you can try and do is say, well, rather than scale up the computation, can we scale down the data? Right? Can we take this vast data set and squeeze it down into something usable and representative that fits conveniently on a single machine, maybe on a commodity laptop? Okay. It's a great aspiration. Maybe it's just sort of science fiction. So we want to generate compact representation of large data sets that we can analyze conveniently on a single machine. Why might this have any possibility to not be fiction? Why is there any hope that we might be able to do something in this direction? Well, one aspect is typically what we finally want from a computation often boils down to something quite small. We want maybe some summary or analysis of the data for a human to consume, some graph or picture that someone can interpret, or some output or decision that we can then act on. Okay, so at least the end outcome is small. So the question is, how quickly can we reduce the volume of data to get to that end outcome? And of course, there's going to be compromises. You can sort of easily come up with simple examples that say, in order to answer this kind of question accurately, if I'm going to squeeze down the size of my data, then I'm going to lose something. Typically, we lose any notion of an exact answer, and we'll get some kind of approximate answer. We lose determinism, and we're often working in the realm of randomized algorithms. And there are certain classes of problems for which we can't even start. Anything that involves sort of recovering specific information about some part of the data, we can't do without keeping all of the data. What we can do is think about things that pull the data together and give some global overview of the data, some overall distribution, some model in the machine learning terminology that is much more compact. And maybe I set this up looking like this is an opposition to sort of large-scale data center computation. It's not necessarily an opposition. It can be very complementary. Indeed, you may still need that data center in order to build your summary. And the question is just, what kind of computations need data center scale computation? What kind of style of computations can work with some compact summary? And again, lots of drawbacks. So this is not going to be a panacea. This is something where we're going to at least begin by looking problem by problem. What are the kind of problems we can solve? And as well as thinking, what are the kind of things that we can't solve at all? Okay. So I'm going to try and keep on time. And I've got this very rough two-part outline where the suggestion was sort of part one is more of an overview, tutorial talking about some of the technical ideas behind this, and in the interest of keeping it reasonably accessible, no proofs, not too much maths, but a few algorithms. And the second part is a bit more high level, talking about some recent work that I've been involved with, so it's taking these basic ideas and then saying, okay, now how do we actually use them for things we might more directly care about? So in the spirit of these things, the first introductory tutorial part has got all the difficult stuff, and the second cutting-edge research stuff is hopefully easier to follow. Okay. So let's step back for a second and step away from the applications, the motivation, and just try and concentrate on this notion of summary. Right? If I want to say I want to build a summary of data that's going to be useful for a particular set of uses, then what properties should it have? What operation should I be able to do with it? Right? So I'm going to think about a summary as being a data structure. So we're in the world of algorithms and data structures. And I want it to be something that I can construct efficiently and incrementally. I want it to be something where I can build the summary looking at different parts of the full data rather than having to see all the data at once in some kind of ramble. So what do I want to do? In the abstract, again, I want to be able to conjure up some new empty summary, update it a single tuple at a time. And if I keep updating my summary a single tuple at a time, effectively I'm in a model of computation called streaming computation, because I can think of the data streaming past me. But I'd also like to be able to take two summaries of different subsets of data, put them together, merge them to get one summary of the union of those inputs that has all the same properties as each individual summary. And if I can do that, I can pretty straightforwardly map it into most models of collaborative distributed processing, right? If I can do that kind of thing, it's going to fit nicely in sort of a MapReduce or Spark type system. And lastly, I need to get some information out of my summary. So I need to be able to pose a query to my summary, and a particular summary is going to support a particular type of query. And it's going to give me some answer, and that answer is typically going to be approximate, so I'll use this parameter epsilon throughout to give some notion of how good is that approximation. So a small epsilon is going to be more accurate, a large epsilon is going to be less accurate. Right. So, our setup is parameterized by epsilon, giving us this measure of accuracy, n throughout as some measure of the size of the data, and we're going to get some overall guarantees, some overall costs in terms of how much space does our summary take up, how long does it take to do each of these operations as a function of these parameters. Right, so that's sort of the game. That's where we want to play. And again, our question is just, now that we've set up the playing field, the rules, does anything exist? Do there exist any summaries that sort of meet these sort of desiderata? Okay, so time for a minimal piece of audience interactivity. Hands up everyone who's heard of Bloom filter. Good. It's a good fraction, so I'm somewhat on topic. And I'll do the usual thing of saying, right, I'll give an explanation that's too fast for the people who've never heard of it before and too slow for the people who've know all about it, therefore satisfying exactly no one. Good. So Bloom filter is, I'm now claiming it as an example of one of these summaries. It has a great history going back to, I think, 1970s, but has sort of come into popular use as sort of one of the few really well-known algorithms for big data computations in the last 15 or 20 years. And it's exactly the kind of data structure you will see in a standard data structure and algorithms course, but with a few twists. So maybe you've seen this idea of a dictionary data structure, something that lets you store and retrieve information. Bloom filter is sort of a restricted dictionary. Right? So Bloom filter lets you take a set of objects, possibly with very large descriptions. So think of like a long list of websites, and we're going to squeeze them down into a bit vector. How are we going to do that? We're going to have a set of hash functions. K, so in this picture K is 3. We've got 3 hash functions. For every item, for every web URL, we're going to apply each hash function to that. That's going to map us somewhere into this bit vector. So I've got some length m bit vector. And to record the presence of an item, I just find all the places where it hashes and make sure that I've got a 1 at each of those locations. Okay? So that's my update operation. What is this summary good for? This summary is good for lookups. It's good for taking some other item and saying, roughly speaking, have I seen this before? And I'll explain what I mean by roughly speaking in a moment. So I've built my Bloom filter by encoding, using these hash functions, a whole bunch of items. And then a new item comes along and I say, have I seen this before or not? So what do? I take the same set of hash functions and I apply those hash functions to this item and I look to see what bit value I see at each location. And then I'm in an interesting situation. So if I see a 0 at any location, that means that this item can't have occurred before. Because if it had occurred before as a part of an update, then I would have made sure there was a 1 at each location. So a 0 is clear evidence that I've not seen this item before as part of an update. If I see all 1s where this item should be stored, I'm actually uncertain. So it looks like maybe I've seen it before, but because of the way this data structure is set up, could have been that a different subset of items came in, one of them set the first one to a 1, a different item set some of the other ones to a 1, so it might be a false positive. And part of the design of this, I'm not going to go into the probability, there's a nice sort of 3 or 4 line exercise in probability, is around saying how do I choose this number of hash functions k and this size of the bit vector m to ensure that that false positive probability is sufficiently small given the size of the set that I expect to work with, that this will not be a problem. And moreover, if I want to use this, then I want to use this data structure in a scenario where if I do have a false positive, maybe it's not so bad. So, a canonical example of Bloom filter uses is in systems involving caching, where I want to know is some item in my cache or not. I do a fast lookup in a Bloom filter, and if I get a negative response, I'm certain that that item is not in my cache, and I proceed accordingly. If it looks like the item might be in my cache, according to the Bloom filter, then I go off to the cache, do a more expensive lookup in the cache, and if I'm wrong, still on average, I've saved myself a lot of time. So Bloom filters are great when you can set them up so that that your true negatives make life better, and your false positives don't hurt too much. Right. And then I talked about how do you update, how do you query, how do you merge two of these things together. So long as you've agreed in advance what the hash functions are, what the parameters of this data structure are, you can merge two together just by doing a bitwise OR. Okay, so that's great. Okay, so that's sort of example 1 of a summary. Lets you approximately represent a set and has this nice trade-off between false positive probability and the overall size. Okay. And I think I said some of this already, so if you go out and look at blogs of people talking about, what are the things you need to know to be working with large volumes of data, Bloom filter is something that comes up a lot. You can do all kinds of games with the Bloom filter. So you can sort of tweak it to let you allow deletions as well as insertions. And it's a great business to be in if you like to churn out papers. I think this was certainly true a few years ago. I haven't checked recently, but for a while you could go to pretty much any networking conference and reliably there'd be a handful of papers looking at some new arcane variation of Bloom filters based on overlapping hash functions or cascades of Bloom filters filtering other Bloom filters and things like that. So lots of fun to be had sort of taking this randomized algorithm and seeing what are all the consequences of it. Okay. I'm contractually unable to give a talk without mentioning count in sketch, so here we go. You can view this idea as generalization of the Bloom filter. It didn't really occur to us that way, but in retrospect, that can be a useful way of viewing it. And it starts with a similar setup, but we're going to go in a somewhat different direction. So now we're going to think about how do we summarize data that is frequency-based. So we have items as before, items from a very large domain of possibilities. But now we want to think about these items having counts or maybe weights associated with them. What we're interested in is understanding something about the aggregate count of an item. So over all the occurrences of the same item, we're going to aggregate, sum up its count. That's going to be its sort of aggregate count. We want to reason about those aggregate counts. Right. So in terms of representing that, the most convenient thing to do is to think of this, that our input data is describing a vector. Right? It's describing a very high-dimensional vector. And we want to build a summary of that high-dimensional vector so that that summary is going to be much smaller than the vector itself. Right. And the main difference between these sketching ideas and the Bloom filter is here that this sketch is going to be asymptotically smaller. Right? It's going to be sublinear in the size of the full input. Typically, for a Bloom filter to be useful for its task, it has to be proportional to the size of the true input, but just, much smaller, so 10% or even 1% of the size of writing the input in full. So here we're going to sort of go even smaller than any fixed fraction. So how does it work? It kind of looks a little bit similar. So we're in this realm of taking data and mapping it into new shapes. So we're going to build this data structure, which is just an array of counts. So W wide, D deep. Think of it as a collection of rows. And again, we're going to use hash functions to sort of map items into this data structure. So how does that look like? So here in this schematic, this sort of picture is trying to show this is our array, W by D again. We have some item whose identifier is J, so J is sort of the index of the item in the input vector. And C is saying we want to add on a contribution of weight C to the aggregate count for this item. So similar kind of thing, what we're going to do is take each hash function. We're going to take the first hash function and use it to map J somewhere into the first row. Second hash function maps J somewhere into the second row, and so on. And just everywhere where that item maps is a counter, we're going to add on the contribution C to that counter. Okay, so that's describing the update operation. Then if I have two of these, merging them together is easy. I'll just add them together entry by entry, again requiring that we have the same shape and the same set of hash functions to add things together. So what good is this? This is something that can look odd because it sort of violates lots of things you expect about hashing, right? So normally in a hash table, you want to hash things in such a way that you minimize collisions and there's room for everything to coexist. This is something where the parameters are chosen so that we cannot avoid collisions. So lots of items will collide. So within one particular cell, I've got all of the mass of a particular index entry J, but also confusing with that is adding up the mass of lots of other elements that hash to the same location. So if I just go and look where a particular element lands, and I look at the count there, I could be really wrong. I've got the count of the thing I'm looking for, but I could have lots of confusion from the aggregation of lots of other counts. So the insight behind this structure is just that on average, things aren't that bad. So on average, we don't expect too much colliding mass. And by doing this sort of repetition over rows and looking at, let's say, the smallest count associated with any occurrence, with any place where element J is hashed, that's actually going to be a reasonably good estimate. And we can sort of formalize that using a very sort of straightforward probabilistic analysis. So it basically says we can estimate the weight of any individual index in this aggregate vector just by looking over all the places where that element is mapped and taking the minimum of them. And again, this sort of thing then lets you keep track of large collections of statistics. And what it promises basically is when the statistic you're interested in is relatively large, when it's some reasonable fraction of the total aggregate count, you'll be able to recover it reasonably well, and when it's small, you won't be able to distinguish it from noise. So it's going to work well if you're looking for things that are significant. If you're looking for peaks in your statistical data. And as a result, it's been used in various places by organizations like, by telecoms companies like AT&T and Sprint, by sort of tech companies like Twitter and Netflix, sort of looking at overall sort of statistics on very large high-dimensional data, but you're only interested in where the peaks are. Okay. So I'll just sort of generalize this a little bit and say this is an example of what we sometimes refer to as a sketch. And when I say sketch, what I'm thinking of is some data structure that I can represent as a linear transformation of the input. That is, if I think of my input is modeled as a vector x, and I build this summary structure of x, then I can write that just as the effect of a matrix S multiplying my vector x, right? So I have some, what I'll call a sketch matrix S, doing that multiplication. If you sort of squint at something like the count min sketch, you'll realize that the effect of these hash functions is essentially exactly this linear operation. I'm taking a linear combination of my input where the sketch matrix S is defined by those hash functions. So using this abstraction of sketches is sometimes useful because it means we don't have to worry too much about certain properties, right? So we get some nice linearity properties that say, if I want to take linear combinations of my input, I can sketch a linear combination by taking the corresponding linear combination of my sketch. In other words, I have this sort of linear composition property, right? So that means that whenever I want to think about these properties of being able to update and merge these summaries, they kind of follow immediately from this kind of one-line argument around linearity. So sometimes we talk about them in terms of sketches and sketch matrices. Sometimes we talk about them, as we did previously, in terms of hash functions. And the reason is just that if I had to write out the sketch matrix S, I wouldn't really be achieving my objective of working in a much smaller amount of space, because if the large object that I'm trying to summarize is vector x, and in order to summarize it I have to keep track explicitly of a very big matrix S, then S is much bigger than x, and so I'm not going to succeed. So what I want to do is sometimes I'll think in terms of matrix S, but for implementation I want to make sure there's a compact representation of S in terms of hash functions. And moreover, I may also worry a little bit about exactly what properties do I need these hash functions to satisfy in terms of giving the guarantees that I want. So certainly I want the hash functions to be sort of simple and fast. To really get into sort of the mathematics of this, you also have to start worrying about what is the real underlying randomness that you need about these hash functions. And all I'll say here is that it's actually, you need very low, very easily achievable random properties of the hash functions, right? So you actually need them to be much weaker than, say, hash functions that you might use in a cryptographic context. Okay. Now let me just sort of take that idea of sketching and add one further twist to get, rather confusingly, something that predated the previous methods. So if I want to do something like, encode a vector and then be able to pull out information about entries, that may not seem like sort of such a challenging problem on the face of it, because you can sort of see this direct connection between the entries and the information you've seen as you're going along to build the summary. What about if you want to do something a bit more complicated? So what about if I want to look at this vector x and learn something about its Euclidean norm, right? Something about the sum of the squares of the entries. Right? If all I've seen is incremental updates to the sketch as I go, to the vector as I go along, it's not obvious what information you would keep to allow you to compute this nonlinear function of the input. And indeed, there's a nice connection I won't go into today to this idea of sort of summarizing vectors in Euclidean space to ideas from mathematics under the name of Johnson-Lindenstrauss lemma, which is very heavily used in sort of data analysis and data reduction and beyond. Okay, so in half a slide, squeezed into the bottom corner, I'll just say here's the hack that you need to do to the last sketch you saw in order to get this, be able to estimate this Euclidean norm. So we'll do one extra twist, which we'll use a second set of hash functions that also apply to each item that I update the summary with. But these hash functions, instead of mapping to a bucket, to a cell in this array, they just map me to a +1 or -1. So I do exactly the same thing I did before. When an update comes in, I use the first hash function h to map into a particular bucket, but instead of adding on the count of that update, I multiply the count by the hash value, again based on index j, and that's going to give me either a +1 or -1. So we either add on the weight of this item, or I subtract it. Okay, so it's a little twist. And then what do I do? Essentially what I do is I just take each row in this array and look at its Euclidean norm. And with a little bit of mathematical magic, you realize that the Euclidean norm of this compressed row in expectation is identical to the Euclidean norm of the vector you started with. Right. I'm not going to tell you why. Play around with some examples to see if you can figure out why in expectation that's true. So it's easy to say in expectation something is true, because when you're dealing with randomized algorithms, what matters is not necessarily the expectation, but how tightly concentrated you are around that expectation. You know, I might be very, very far away from the expectation. So I also need to reason about things like the variance, how much uncertainty do I have, and you can show that that variance depends rather neatly on the width, this parameter w. And then to get from something which essentially says, on average, I'm pretty close, you know, 2/3 of the time, to something that says I'm guaranteed to be close to the right answer 99% of the time, or 99.9% of the time. I do an extra trick by taking the median of the rows. So each row I take its Euclidean norm, and then I take the median. And again, there's a sort of a nice argument based on ideas from Chernoff bounds to say why taking the median is a sensible thing to do. So without getting sort of too tied up on the details of the algorithm or why it works, the observation is just using a relatively simple sketching technique, I can start to summarize information about high-dimensional Euclidean spaces, and this is sort of the starting point, which we'll come back to in a little while, of why summary ideas might be useful in data analysis machine learning, where we often start to model our data as existing in some high-dimensional space, and we want to reason about it there. Okay. So that variation goes under a number of names. As a community, we seem to have settled on calling it the count sketch, for giving us this Euclidean norm estimation property. Okay. So one more summary before I sort of start going into building more things on top of these summaries. So L0 sampling. It's a fancy name and a slightly tricky definition that's actually trying to capture something very simple. So again, think about a scenario that we can represent as our data is captured by some high-dimensional vector. And what we'd like to do is sample indices from this vector, so indices I, from our implicit data vector according to some distribution. And what this really says is sample close to uniform from the entries in the vector that are non-zero. So if you have a vector with dimension 1 billion, but you only have 1 million locations in there that have a non-zero entry, either a positive value or a negative value, just pick almost uniformly, or as close to uniformly as you can, one of those 1 million non-zero entries, and never tell me one of the non-zero entries. Right? It's a little bit of an abstract problem. Maybe it's a little bit tricky to see what it's for, but we'll come back to that in a few slides' time. Right. And again, the main challenge here is we're looking at data where we have increments and updates. Some of our entries are positive, some of our entries are negative, and we're trying to keep track, trying to be able to perform this sampling operation. So in fact, some of the ideas that are used date back more than a decade, and were formalized in subsequent work to apply to this problem. So the basic idea is the following. I'm going to think about having a sampling operation that works on my data vector, so that I sample elements, I sample indices without regard to whether they are populated or not. So this is sort of a static process, but I'm going to sample with some probability p. That's going to create a subvector just of those sampled indices, and I'm going to feed that to another sketch data structure, which I'll call k-sparse recovery. K-sparse recovery has the property that if the number of non-zeros in the vector that it receives is smaller than k, then it keeps information that lets me retrieve that vector exactly. And if the number of non-zeros in the vector that I give to this data structure is more than k, then it just says, fail. Okay. So I'm not going to go into too much detail on how you construct a k-sparse recovery structure. All I'll say is if you think about the sketching ideas we've seen already, they get us most of the way there. So if I take a count min sketch or a count sketch and I give it a vector which is very sparse, which has very few non-zero entries, such that my sketch is actually bigger than the number of non-zero entries, then there's enough information within the sketch to decode and recover that vector. Right? It's only going to work when we have very sparse vectors. But then the whole trick of this L0 sampling approach is to say, well, your full data vector might be very dense, so I'll subsample it and subsample it and subsample it, and some sampling rate is going to make it sparse, and that sparse version of the vector I can recover, and then I'll sample from that sparse recovered vector, and that's going to be my L0 sample. So here's the picture, right? These sort of colored dots are representing the non-zero indices in my vector. At the bottom here, I'm saying this is when I sample at probability 1, I just pick up everything, but as I geometrically reduce my sampling rate, there'll be some level where I've got down to a sufficiently sparse collection. I could do my k-sparse recovery and then just uniformly sample one of those, compose all the probabilities, and argue that what I get is a uniform sample. Okay. And again, there's a bit of sort of mathematics, a bit of work to do to show that this meets the sampling definition. But, with some work, it all works. Okay. So what have we got so far here? We've got this problem that I invented and didn't really motivate very well, and a weird-looking data structure that I claim solves it. So let me try and tell you just a little bit of an example about why this might sort of fit into something else. So the summaries I've talked about so far have all been looking at data that I can reasonably represent as a vector. So let's go for something a little bit more challenging. Let's think about a graph, which at the very least needs a matrix, an adjacency matrix to represent. And if my graph is very big, it's going to be unwieldy. So I want to think about what kind of summary technique can I use to summarize this graph and learn things about it. So we'll start with something very simple. We'll start with connectivity. That is, we want to be able to find connected components. So I've got a massive graph defined by a large number of edges that I see incrementally, and maybe some edges arrive, some edges depart, so everything's a complete mess. How can I use a summary to learn which nodes are connected to each other in this undirected graph? So if I had plenty of computing resources, and I didn't want to do any of this summarization stuff, how would I solve this using Java, using sort of fairly standard computational setting? A few different algorithms. This one is I think, a version called Brovka's algorithm. Basically says, okay, start off treating every node as if it's in a component all of its own. And then for each of my current components, if there's some edge going out from that component to another component, then actually it's not two different components, they're linked, so they're one component. So contract that edge, put together all those two components and say this is my new component, and keep going until there are no more outgoing edges from my components. Right? So just assume everything's in a separate component and keep merging things together whenever I see a violation of the assumption that everything is separate. All right, how would you take that algorithm and instead of doing it using RAM model and exact computation, how would you do it using these kind of summary structures? Well, what you could do is you could build an L0 sampling data structure for each node where it encodes the adjacency list for that node, so all the adjacent nodes for this node. And to get me started, for each node I could sample from that sampler, and that will give me some outgoing edge for this node. So it will tell me some neighbor of this node, and I can merge those together. Then I can use the linearity, the additivity property of the sketches to say, okay, now I've got two nodes that I know are connected. So I will add their sketches together, and that basically adds together their adjacency lists. And now I can sample from that compound adjacency list, so the adjacency of this connected component, and learn about further things. And I can iterate this and start to learn about the whole graph. So there's a problem with this, right? So if I do this if I've learned that some large number of nodes are all part of one connected component, and I add together all their adjacency lists by adding together the sketches of their adjacency lists, and I sample from that, at some point, I'm not going to learn any new information. I'm going to learn, hey, there's an edge between node I and node J, but I already knew they were in the same component. Right, I'm only going to learn edges that are internal in the component, whereas what I'm looking for is I'm looking to collect edges that are outgoing from the component. So does this kill off this algorithm? Does this destroy this algorithm? No. So there's a nice trick due to Kukjian, Sudipto Guha, Andrew McGregor a few years ago, where they basically said, we can solve all this with a little twist in the encoding. So every edge in a graph in this algorithm gets encoded in two places. So an edge between I and J gets encoded in the information of node I and gets encoded in the information of node J. What we'll do is we'll use a different encoding. So we'll encode this edge as a +1 weighted edge for one of those nodes and a -1 weighted edge for another of those nodes, for the other of those nodes. So that if we decide that node I and J are in the same component, and we add together their sketches, that means we're adding together their adjacency lists. And we set things up so the +1 for node I and the -1 for node J line up in our indexing system and cancel out. Right. So we use this clever encoding. What we actually get is we can then take these sketches for a collection of nodes, add them up, all the internal edges cancel each other out, disappear, and what you're left is with a sketch that's only encoding the unbalanced edges, that is the outgoing edges from our component. Right. There's some technical details to work through here to reason about how many different sketches do you need, right? To reason about how do I make sure that I'm not violating some information theory bound and somehow encoding the entire graph in a sublinear amount of space. And the basic insight is to say that we should view this whole process as proceeding essentially in parallel for a number of rounds. So in round 1, every individual node tries to pair up with a neighbor. And in round 2 of the current collection of connected components that we have, every connected component tries to pair up with another component. So that in expectation, we only need a logarithmic number of rounds to collapse down to the true connected components in the graph. And then we use sort of a fresh set of sketches that we compute all together at the start in order to support that algorithm. So what do you get? You get the fact that for any graph that may have quadratic number of edges, you only require a small amount of space that's essentially logarithmic per node, so n log n polylog n space in total, to solve this connected components problem. Again, it's perhaps surprising that, for something which looks very complicated, there is this fairly oblivious algorithm. The information you collect doesn't look very closely at the graph, it just scoops it up and follows the hash functions that lets you solve this problem. Okay. So what that's trying to say is that we have this idea of summarization, we have this idea of summaries. We started building them for vectors, and then we can start, in this line of work starts going off to look at graphs, and there's an associated body of work that says what are all the things you can do with graphs using sketches. So equally, you might say, what about other objects? Okay, if we can do vectors, can we do matrices, can we do tensors, can we do all kinds of linear algebraic things? So the answer is yes. Let me give a quick example. So let's suppose that I'm interested in matrix data. What's the most basic thing that I could do with matrix data? I might want to learn something about the product of two matrices. Right. So I want to build up some representation of what's the product of two matrices given some compact summary of each matrix. And I'll use this sort of entry-wise norm called Frobenius norm to measure the error. So in other words, I'll just look at the error and the difference between the true product and my approximate representation, square that error for each entry and add it up. Okay. So on first glance, this looks like a tough problem. Looks like we're going to need some fairly new heavyweight machinery to solve this. But actually what I'm going to try and argue is that with the sketches we have already, you can do a good enough job. Right. So what do? You build the count sketch or the AMS sketch of each row of the first matrix, each column of the second matrix. And basically, using a tweak of what we've seen already, you can take those two sketches of a row and a column, combine them, and get a pretty good estimate of the inner product of those two vectors. Right? And then all you have to do is say, well, collectively, every entry in my matrix product is defined by an inner product by a different row and a different column. So let's just materialize all of those. And when I add up each of those individual errors, it will add up to something which is not too bad overall, at least in terms of the norm that I've set this up in. And this was sort of formalized and outlined about a decade ago with some tweaks. So I've given you sort of the vanilla baseline version of this. To kind of squeeze the most accuracy out of this, you want to do something a bit more complicated, use the sketches in a slightly different way. But at its essence, you have your baseline result just by saying, take the sketches you have already for vectors and decompose your matrix computation into a computation over a whole bunch of vectors. Okay. So that's been improved on a bit, and based on using more complicated hashing functions and sort of a higher degree moments argument. What we'll come to in the next section is to say, okay, well, maybe I care about matrix multiplication, maybe I don't. If I want to start thinking about building models for my data, then I want to start moving in the direction of things like regression. So let me give you sort of a taster for regression, and we'll come back to this in a few slides' time. If I want to solve a regression problem, that's basically I have a data matrix A, target vector B. I'm trying to find what is a vector of coefficients X that sort of solves this minimization problem, so minimizes the difference between A, X, and B. This is potentially costly, time-consuming to solve if I work in the full original data domain. So what I'll do is I'll sketch the matrices to reduce from n rows down to some sort of d squared over some polynomial in d number of rows, and essentially come up with a new version of a regression problem, and I'll solve that regression problem using the sketch data instead of the full data, and then argue that that actually gives me a good answer. And a whole bunch of other work in linear algebra ongoing that I don't have time to get too much into. Okay. In fact, there's a whole survey that sort of sets out, book-length survey from David Woodruff that sort of sets out the basic ideas behind, this idea of sketching as a tool for linear algebra. Okay. So in the interest of time, I'm going to sort of skip quickly on. So I'm just going to very briefly say, I've talked a lot about algorithms. I've talked a lot about constructions. There's an entire parallel line of work that also says, what can't you do? How do you construct lower bounds? And that goes into communication complexity and information theory, sort of argue that there are some functions for which you can't construct any summary that gives any kind of guarantee. Okay. So that was the slightly longer part one. Any questions so far before we move on? Okay. Yeah.
Is there some intuition for the kind of problems that sketching-based techniques work well for? Or is this something that don't work well for, and why? I mean, what's the fundamental? Because it seems like you've got this algorithm and they just kick it and it gets something very nice out.
Yeah.
Sometimes you kick it and it won't.
Okay. Yeah. So the question is, what's some intuition for what works and what doesn't work in sketching? So in the crudest sense, sketching works well for when you're trying to evaluate some function that depends on relatively coarse features of your data, right? Things that after some transformation will stick out. And the counterpoint to that is where it is absolutely hopeless is anything where you need to go and look at any small, very focused location within the data in some detail. So anywhere where I kind of need to go back and say, so at index XYZ, was there a 1 or a 0 there, right? And so corollary to that is that you then show that kind of argument essentially by appealing to information theory, by saying if the information that I'm extracting from my summary is sufficiently large that I could sort of reconstruct a large fraction of the input or reconstruct some encoded large input, then the number of bits of that input is a lower bound on how big my structure has to be. So you can take that argument and apply it back to Bloom filter. Right? I sort of made this distinction between Bloom filter and some of the other summaries, and said for a Bloom filter to work reasonably well, you need it to be somewhat proportional to the size of your input. And it's for exactly that reason that you're actually using Bloom filter to answer these sort of presence or absence kind of questions. Whereas for these other things where you're computing some aggregate over the summary or so on, you're less dependent on any individual part of the input, and your approximation space, your approximation guarantee, gives you lots of room to have forgotten lots of stuff. So it's all about sketching and summarization works when you set up the problem to allow you the opportunity to forget. Okay. So let me go on and talk about two recent works where we've been trying to take summary ideas and think of them for sort of data analysis tasks. So the first one is a distributed model. Right? Think of this as a cooperative distributed setting. So as far from Byzantine as you can. So everyone now in this scenario is going to work together. They want to build a model of the data. And what we're interested in is saying, how do we build this model? over data that's distributed without incurring a high communication cost. Okay. So let me sort of say a little bit about the model first. What's our model? So we have some number of sites who are each observing streams of data. And they're going to interact with one centralized coordinator who's going to maintain the model centrally. And we want to bound how much communication has to go on between each site and the coordinator. In this model, we're going to force all the communication to go through the coordinator. It turns out we don't really lose out by doing that. And we might also worry about how much computational effort does each site have to invest. So, this is interesting because we're doing this sort of in an ongoing fashion. So it's sort of continue being updated over distributed data, which is streaming in, and we're trying to evaluate functions which are over the entirety of the data rather than any sort of sub-piece. What's the model? Okay, not the most extravagant or cutting edge, but let's start with something. We're going to look at Bayesian networks. So we're going to say we're given a Bayesian network as a graph that says, here are the variables of interest. Nodes represent random variables. Edges are telling us something about the dependencies. And we want to instantiate this model based on the data that we observe. So what exactly do we need to find out? Right? So we're given the graph, right, that says this is how we believe these variables are conditionally independent. But in order to use this, we also need to collect the statistics. Right? We need to essentially build up these probability tables that tell us for a particular combination of parent nodes, this is a sort of very simple binary example, we have certain probabilities of particular outputs. And once we have those conditional probability tables, we can then predict, for a particular example, what the outcome would be. We can do various kinds of inference tasks. So the focus here is on the seemingly simple task of just saying, how do we instantiate these conditional probability tables over this distributed and evolving data? Okay. So in essence, the reason we can make any progress at all on this is that this isn't such a difficult problem to set up. What we want to do is build just the empirical conditional probabilities. That is, we want to look over the data as it arrives and just count up how many times do we see each combination of parent values in conjunction with a particular variable's value, and then turn those into probabilities. Okay? So doing this sort of on a one-time basis wouldn't be too bad. We'd just get everyone to build those tables on their local data, ship them up to the coordinator will just add them up, and that will be the empirical model. So what's interesting here is just that we're saying the data is evolving over time, and we want to build this up as time goes on. So we may have had some previous set of values, then we see some new update that updates our local counts. It's going to update our local probabilities, and we need to keep the central coordinator up to date with what's going on. So you can sort of pause for a moment and think, well, how would you solve this when your objective is to bound the communication cost? So the naive starting point is just say every time any local site sees any update, tell the coordinator about it. So the cost is proportional to the number of events that you observe, and then you say, well, do we really need that? Do we really need just to basically mimic the centralized algorithm by aggressively informing the coordinator every time something happens? Probably not, because we don't actually need these counts to be exact and up to date, right? If I've seen 1,000 events and 500 times a particular outcome happened, then if that happens one more time, then 501 out of 1,001 looks pretty much like 500 out of 1,000. So not that much is going to change in my model if I work with the old version than the new version. And anyway, more sort of hand-wavingly, I'm somewhat subject to random variation in the order of events anyway, that I'm going to expect a little bit of variation in these probabilities. So I don't need to know the exact counts. I just need to have a reasonably accurate, approximate idea of what's going on. So this is great because this lets you then sort of think about a nice, clean, abstract computer science problem. How do you count approximately over distributed data in this sort of in this coordinator model and minimize communication? So for a problem that to me seems sort of so fundamental, so basic, it's sort of interesting that it wasn't really formalized and studied until a few years ago. But there's a very nice randomized algorithm that does the trick. So essentially, think of just one site on its own that's counting some event, and it wants to keep its coordinator up to date within some accuracy threshold. So every time this site sees a new event, it tosses a bias coin, the probability p, and if that coin comes up heads, it reports the current count, and if the coin comes up tails, it just keeps quiet about it. So we've introduced some lag into this system. Again, thinking about this as a distributed setting, I've kind of abstracted away all elements of synchronization, synchrony, and so on, just to say algorithmically what's the problem here. So if we do that very simple coin tossing algorithm, then you can build an appropriate estimator for what the count should be estimated at the coordinator who's receiving these sporadic updates. So essentially, their belief about the count is the last thing they heard plus a correction factor for how many updates they think they might have missed. Okay. So you can take that estimator, you can do the usual kind of things you do with random variables. You can show it's unbiased. You can analyze its variance and show that it's not too large as a function of this parameter p. Right, so the less likely you are to report an update, the higher your variance becomes. So then moving back towards our setting, how do you set this parameter p? So what we'd like to do is say, relative to the total count, this sort of this n here, we'd like to guarantee we're only uncertain up to some small fraction epsilon of this. So what we should do is set p as a function of the number of sites k divided by epsilon n. And then we hit an interesting kind of circularity here, because we're saying our overall goal here is to try and estimate what n is, but our algorithm depends on n. Okay, so what do? Again, we just sort of relax a bit and we say, well, it doesn't really matter. If we're a little bit cautious here, it's fine. So if we send with a probability higher than this theory says, that's fine. We're still going to be correct. We're just going to be more accurate than we need to be. And so we can sort of progressively relax our sampling rate. So when we start with no information, we can just say we'll sample everything till we get off the ground. And then as time goes on, we go, actually, sampling with p equals 1 would only make sense if we had a very small number of items. We know already we've got a larger number of items, so we'll relax the counting. We'll drop by a factor of half. Right? We'll go from sampling everything to sampling every other update. And you sort of combine these observations and analyze this and basically say that over all of this, your total communication costs count up to n in this distributed fashion over k different sites. Looks like square root k over epsilon. And essentially square root k over epsilon is basically what you would have got if you'd got the exact right p from the start. Plus k log n, and k log n is basically just the cost of stabilizing and finding the right p sampling value. Okay. So we've kind of come a long way from where we started looking at graphical models to sort of this very basic counting problem. Let's sort of go back up the stack and say, how do we plug this all together? So we now have a primitive that lets us estimate a count. How do we use that within our algorithm for learning the parameters of this Bayesian network? we plug it all together. What I'm interested in doing is giving an overall guarantee on this ratio of probabilities, right? This p tilde over p hat, where p hat is sort of my maximum likelihood estimator, which is just what I would get if I used the exact counts. P tilde is what I would get if I used approximate counts. Epsilon here is this overall guarantee that I want to give, so I want to sort of bound this ratio somewhat close to 1. And the issue is basically I'm not just counting one thing, now I'm counting a whole bunch of things. Right? So what I'm actually doing is if I sort of expand this out, looks a little bit hairy, but essentially there's not too many things. And I'm also slightly confusing things further by mixing up my variables, so try not to worry too much about what variable means what. But essentially, for every one of n different variables, I have a pair of counts that I need to keep track of for any particular inference goal, which is I need to keep track of some count to do with the joint distribution of a variable and its parents in the graphical model, as well as the count of just the parents. Okay. So I just have to introduce a whole bunch of other variables. So I've got a whole bunch of approximation errors, which are going to be the parameters of the approximate counting algorithms for, in this case, it's for the joint distribution of the variables and the parents, and another collection of approximation factors for just the parents. Right? So I have a whole bunch of parameters. There's going to be some constraints on these parameters to say, if I meet these constraints, then I'll give an overall guarantee on accuracy. Right? Which is basically that. So I need to choose my alphas and my betas so that when I multiply this thing together, and the reassuring thing is that I've sort of removed anything about the data here, I just need this overall guarantee on the parameters, I get this overall guarantee. And essentially now we're just into sort of strategy exploration, right? So there's a few different strategies you can try. A relatively simple one just says, think of each of these alphas and betas as sort of a fraction of a budget that I'm going to divide up. I'm going to use some sort of simple bound and just say these budgets have to add up to my overall error guarantee. Right, so set all of these approximately proportional to epsilon over n. So here n is the number of variables, so sort of a 1 over n slice of the total error guarantee for each variable. That actually misses something quite important, which is things would be very pessimistic if all of the errors went against you. And actually we're reasoning about errors that are coming from unbiased random variables. So rather than essentially bounding each random variable independently and composing those bounds, what we can do is just look at sort of a random variable that's the sum of all those random variables and look at its total variance. And when you view it through that lens, you can actually get a much better result that says actually you only need your alphas and betas to be proportional to a 1 over square root n fraction of the error guarantee. And the last twist on this is to say, well, some variables have many possible values, so they're high cardinality. Some are low cardinality, maybe they're just binary. And the accuracy that I get is going to depend somewhat on the count that I see for particular attribute values overall. So I might do some very simple modeling and say basically for higher cardinality attributes, I would expect the counts to be lower on average because they'll be spread across all the possibilities. And I can adjust the accuracy parameters that I give to those anticipated low counts rather than the ones that I might anticipate to be high. Right, so you get a little optimization problem, nothing too dramatic. And when you stick it together, you get these kind of things. So already things look a little bit disorienting in this summary table. Basically what this is saying is if I try to analyze something about the worst case communication cost of tracking this information, if I don't really do anything, if I just centralize all the information, then I've got a communication cost that depends linearly on m, the number of observations, and n, the number of variables. If I do this simple uniform division of my error budget it drops to n squared times log m. And if I use that tweak based on thinking about these as random variables, drops further to n to the 3/2 times log m. And in using that sort of more complicated modeling thing, I get some fairly ugly things that don't fit neatly into a table, but are no worse than the uniform case. So whenever you're doing research and you sort of get to a situation like this that you as the author of the work can't really figure out what's going on, then there's only one thing to do, and that's run some experiments to try and figure out what it actually means. So here's two plots for different networks where we generated a whole bunch of data based on these networks and sort of ran it through this distributed system. So what we've got here is we start off with our horizontal line at the top that says this is our error budget. This is where we want to be in terms of error. So anywhere below this, we're good. And so without looking at communication cost or any other costs, all of the methods are comfortably below that error budget, so everything's good. So what this is saying is as you go through these different methods in order of sort of increasing complexity, the error that you observe based on sort of some ground truth model creeps up slightly, but you're still so far below the guarantee you want to meet that you're happy. Right? Now let's look at it in terms of what's the communication cost. So we did this in a fairly sort of applied setting. You know, we rented out a bunch of machines on Amazon Web Services to try and capture, you know, the true latencies in a real network situation, and viewed this as saying, well, what's the total end-to-end training time of this as a surrogate for what's the overall communication cost. And what you see is compared to the exact approach, you're up to a factor of about 3 improved on that. The baseline approach drops down, and the uniform and non-uniform approaches give the lowest result. The non-uniform approach is marginally better than the uniform, but given the extra complexity, maybe it's not worth it. Just stick with this sort of relatively simple uniform division of error guarantees. Okay. So great, you know, we took a problem that is sort of maybe just a tiptoe in the direction of building a useful model. Thought about how do you maintain the statistics that you need to instantiate that model. And you know, once you've got a Bayesian network, you can do all the kind of things you'd like to do with that, whether it's sort of inference, whether it's classification. The real sort of problem to be thinking about here, though, is at the very start we made this simplifying assumption that says we know the graph for the graphical model, right? Maybe that was far too generous. So, you know, open problem, thing to be thinking about here, other classes of models, or in particular, you know, as a first step, if you just see the data, how do you do that, the graph learning part of it first? You know, we assumed, oh, you're given the graph by an expert, or you just learn it offline on some sample, but more generally, you want to be doing your entire sort of end-to-end modeling and learning online. Okay. Have a few minutes left for sort of 1 second example, and then I'll start to wrap up. Okay, so let's go back to linear algebra. And let's go back to regression. I promised you we'd get back to regression. So lots of data analysis relies fairly critically on modeling your data in some sort of linear space. And even for sort of relatively simple problems, getting into more complex problems, the magnitude of your data is painful, right? You'd love to take your data and start looking at covariance matrices or start looking at sort of matrix factorizations. And once your data gets big enough, that becomes sufficiently painful that you can't just assume you have all the eigenvectors. You can't assume you have any particular factorization. You have to sort of devote time and effort to say, how do we either generate those efficiently or avoid the need for them? Okay, so let's make that specific. Let's think about regression. So standard least squares regression says, again, we have our data, n rows, n examples of dimension d data and our target vector b. We want to sort of find our parameters x. And we said already that we know ways of doing this using sketching. So let's make our life a bit more difficult. Let's actually go into constrained regression, which is effectively identical to regularized regression. So we might want to say, in addition, we don't just want any vector x. We want to only consider those vectors x that lie within some convex set C. So we're going to restrict the solution space. And offline, if we have the time, the space, and the energy, we have tools from convex optimization that for many reasonable classes of convex constraint C will do a good job at some higher time cost than just the least squares. Okay. So what that says is if the instance of our constrained regression problem is small enough, we can solve it. But we want to know how do you handle instances that are much bigger. So there's one approach which is called sketch and solve, which is essentially what I talked about already. It says, take the entire instance of regression, stick a sketch on the front. Use this duality that I mentioned before between these sort of notions of sketching defined by hashing to do it efficiently, but mathematically you view it as a matrix multiplying your setup, and solve away. And what you find is you can solve this, and you can find a solution that's reasonably good in terms of its cost. Sometimes you want more than that. Sometimes you want not just something whose cost is good, you want something which actually gives you something which is close to the target vector itself. So a couple of years ago, there was a very nice paper called Iterative Hessian Sketch that introduced this idea of a different approach, which still uses sketching, but now uses sort of multiple steps of sketching. And essentially what it says is, I'm going to iteratively try and find solutions. So I'm going to hope that my solution xt is converging on the true solution. This is the slightly scary looking equation that describes the step. So within each step, I have to solve an instance of a constrained regression. So I'm solving my constrained regression, but on something, here it is, yeah, something that's much smaller than the original instance. So something where I've applied sketching to reduce the dimensionality. Right. So that's very good. What is it that you need to make this work? You need some properties on your sketching matrix. So you need a couple of technical properties around properties of these sketches viewed as matrices. And in the original paper, it was shown how to do this for a couple of different sketching constructions. So sketches that are based on Gaussian. So you think of your sketch matrix as every entry in your sketch matrix is sampled from a Gaussian distribution. Right? You can prove lots of stuff about those kind of sketches, but there's a big problem, which is that when your sketch is that big and dense, it's a huge amount of information to remember because it doesn't have a compact representation, and it's really slow to work with. Right? So you don't actually want to use Gaussian sketches. So there's one other approach that's known that meets these conditions, which is called subsampled randomized Hadamard transform, which is sort of a sketch which has a nice factorization as a bunch of sort of simple operators that are easy to operate on. And that works fairly fast. So what we did is we took the count sketch that we saw way back at the beginning and showed that this also works. It also has the right properties in terms of sub-Gaussianity and spectral bounds for plugging into this IHS, this iterative Hessian sketch. Then we did something a little bit naughty, which is if you plug in count sketch and set all the parameters so that it gives you a strong guarantee, then the size is a little bit bigger than you'd like. So we said, okay, that's fine. We'll just run the sketch, tuning down those size parameters. So we're going to run the sketch outside of the realm in which it's supposed to operate. And we'll sort of try and argue that although on any given iteration it therefore might not quite do what it's supposed to do with a tight guarantee, it's fine because essentially on the next iteration or one of the subsequent iterations, we'll make it back up again. In other words, we're going to sort of break the conditions that we need on each iteration, but in aggregate we should work. And when we do it like this, things are going to be, we hope, really fast when the input data is sparse. Right? So the nice thing about count sketch is that because you can view it as sort of you take each non-zero entry in your data and do a few hash functions, it's super fast, particularly when your data is really sparse. So let's actually see what impact that has. So we picked one sort of simple constrained regression model, which is Lasso. So Lasso is it's a standard L2 regression with an L1 regularization, and you can view that as essentially as encoding a set of convex constraints. We threw a bunch of synthetic and real data on it. It doesn't matter too much. The main thing is just that this data varied from essentially fully dense data, so almost every entry is non-zero, to ones where a small linear fraction of the data is is non-zero. And again, we sort of did this sort of slight cheat. It said, well, how big should our sketches be? We're going to run them outside of their realm of safe, guaranteed operation, but see what happens. Okay, so here's one view of what happened. This is on synthetic data. So there are two pictures here. The picture on the left says, because it's synthetic data, there's the picture on the left is saying there's the data, and I can see how well can I do compared to the best I could possibly do on this particular data instance. And that looks, worryingly good. You're getting into, with an error of like 10 to the minus 20 something, right? But that's kind of misleading because it's just saying you can fit this data very well. Because it's synthetic, we've got the model that generated the data. So we're saying, well, actually, how close are you getting to the model? And there, maybe sort of more reassuringly, you're getting within sort of this characterization of the error of like 10 to the minus 1. So you are converging on the model, and essentially down here you've sort of basically found the model as well as you're going to find it. And here what we're counting on the x-axis is iterations, right? So if I count up the iterations, it looks like this previous approach I mentioned based on subsampled Hadamard transform is going to be the thing that you want. But actually we don't want to count iterations, we want to count time, speed. So when we switch to wall clock time, things flip in a sort of interesting way. That these dark lines are the Hadamard-based approach, and it's sort of getting there slowly over a number of seconds on these real data sets. But the sketch-based approach using count sketch is just zipping there really quickly. And interestingly, we're getting there faster with a bigger sketch, right? So in other words, the price that we pay in time for working with a larger sketch data structure is more than compensated for by the number of iterations being much fewer. So you do fewer iterations on larger sketches, and you just get there more quickly. So this is really encouraging. This is sort of some evidence that using sketching in a relatively non-trivial regression problem is something useful to do. Okay. Good. So let me sort of just wrap up in the last couple of minutes. So what I've tried to do today is sort of introduce this notion of data summarization, try and convince you that things exist, that initially at least the algorithms aren't too horrible, and as a result they're relatively practical and implementable. And at the downstream end of things, you can actually solve somewhat non-trivial problems with them. So again, over the last several years now, people have been looking at these ideas and related ideas from mathematics to understand other kinds of questions about high-dimensional objects, and you can draw a line between this sort of summarization view of the world and the explosion over the last 15 years of work on compressed sensing and signal processing, on ideas from versions of sort of a sparse fast Fourier transform and others. What we'd love to have would be to say take any arbitrary numerical linear algebra computation, switch everything into a sort of a sketched set an operator based on sketches and run it. We're nowhere near that yet, but we do have lots of insights and understanding of how you can do a whole bunch of linear algebra computations. I mentioned regression, but any other kind of factorization and summarization using sketches and sketch-like ideas. I have interest in using sketching-related ideas for checking computations, sort of essentially doing algebra on sketches or fingerprints to check that the full computation you got looks close enough. And you can take, we talked about graphs and matrices, you can go off into the realm of geometry, points, point clouds, all kinds of stuff. You can go into different computations. You can start looking at the combination of summary techniques and privacy. If I'm lucky, the next speaker might say a word or two about that. So there's lots of current open directions. Okay, so I started with this maybe slightly tongue-in-cheek provocation, saying you can either scale the computation up or scale the data down. There's the kernel of truth at the heart of that is to say that there are a lot of things you can do using a representation of data much smaller than the full input. And we're sort of building up this argument that says, in particular, in various optimization machine learning scenarios, you can get scalability over exact exhaustive solutions. And there's a whole lot of open problems. At the moment, a motivator is machine learning and linear algebra, but it could be pretty much anything else. So with that, I'll finish up. Say thank you very much. Thank you.